Welcome back, everybody. Today we're going to be beginning Unit 2, Differentiation and the Definition and Basic Derivative Rules. So today's topic, 2.1, Defining Average and Instantaneous Rate of Change at a Point. And again, the learning objective for today is determine the average rate of change using difference quotients. So remember, quotient is just a division, pretty much. So we start to talk about the instantaneous rate of change. So we first, to understand it, we got to compare it with the average rate of change. So first, let's understand what a tangent line is. So what is a tangent line? Examples of tangent lines drawn to a curve f of x at a point P. So here you have this graph, kind of looks like a parabola, right? And then the line P right there, the line is touching at point P. Same thing right here, y equals f of x. This is a line tangent to it. All right, and we'll talk about a little bit more about what it means to be tangent. And also this line is tangent at point P. And then note, although many times we might say that a tangent line drawn to a curve may only touch the curve one time, that is not entirely true. So a secant line, by definition, is a line that can intersect a curve at least twice. So misconceptions about tangent lines. So writing a formal definition of what a tangent line looks like is often problematic. The following four misconceptions can be helpful when deciding whether a line is tangent to a curve. So the misconception number one right here is that, okay, so if it's touching at one point, right? Some of you guys may think that it's okay for the graph to go through it. All right, so that is a misconception. A line tangent to a curve if the line crosses the curve at one point. So that's not always true. Although line L touches curve C at one point, line L is not tangent to it, right? It's going through it. So it has to be touching somewhere at least at one point. Misconception number two, a tangent line to a curve must cross the curve only once. So it doesn't actually, here it shouldn't be crossing. It can cross it, right, sometimes. But here it's tangent at point P, and if you notice, it crosses over here twice. So line L is tangent to curve C at point P, despite the fact that line L crosses curve C at two other points. So this is, again, particularly fine as long as it's tangent somewhere on the line on one point. Misconception number three, a line is tangent to a curve if the line touches a curve at one point but does not cross the curve. So here, if we notice, we have it does have an endpoint right there where it's touching at point P, but the problem is like it's not literally what our definition of tangent is here. This wouldn't qualify. So again, although line L touches curve C at point P, it is still not considered a line tangent. And again, misconception number four, a tangent line to a curve is a line that just grazes the curve at one point but does not cross the curve. So the example above, line L is tangent to curve C at point P, despite the fact that it crosses a curve. So it's still touching here, even though it's still going to cross over here somewhere eventually, right? So that's pretty much what we define what a tangent line is. So the tangent line problem, so here's an activity for you guys. Begin with graph of y equals f of x. So step one, let's begin with an arbitrary point and call it c comma f of c, which is what we have right here. Then let's choose another point on the curve that has a horizontal distance of delta x unit to the right of our initial value c. So anything to the right of our initial value c, let's say our point is right here. So that is exactly, so delta x distance, all right? Delta x, remember, is just the difference between the lowest and the highest point right there. So for now, let's call the new points x comma f of x. So this is x comma f of x. And then place this point on your curve, preferably close to the right edge. Connect those points. What is the slope of the secant line joining those 2 points? So if we connect these 2 points, we create a line. How can we find the slope of this secant line? So write it down right there in your notes. So in this case, we're going to call the slope of the secants. And if you guys remember, slope is rise over run, right? Basic stuff from IM1. Rise over run. So in this case, our rise happens to be the difference between our y values, which in this case is f of x minus f of c. And then the difference in in x, which is our run, right, is going to be delta x, which in this case is just going to be x minus c. In step 2, now just for kicks, let's our second x value from above move closer to the original x value of c, reposition the point so that it's about half as close to f of c, and then connect the 2 points. Do we still see a secant line? So in this case, let's move it half the distance, so we were about 4 on top right here, right? Half the distance would be 2, so that's our new points. And then what do you guys think? Do we still see a secant line? So in this case, we still do, right? So is there any difference in the way we calculate its slope? So let me see if I want to calculate the slope. So m secant of this line now, right? Let me make sure it lines up with the other one at least. There you go. So this is still x comma f of x, and then this value, so still exactly the same thing, right? So x minus c, difference in y's over the difference in x's. And then for our last step, it says right there, since we are having such a blast moving our second x value closer to c, let's move that value, that x value, so that it almost touches c. So reposition x comma f of x so it lies right next to c comma f of c and connect the 2 points. So if we get as close as possible, right, the smallest distance we can get is almost something as close to 0 as possible. So it's going to be right here. So that's going to be our new line right there. And then do we still see a secant line? Now in this case, technically still yes, right? So yes, we still see it. Right? There's still a small gap of a distance between x and c, right? A really tiny distance. And then how can we perceive the slope now using a very important concept from Unit 1? So if we want to get really, really, really close to something, right? If we want to approach a certain value, now that we've been using those and we know how to apply them, this is where we can see that the slope of the tangent line, right? If that distance gets so close to 0, that means that x and c are literally the same points. We can do that by finding the limits of, as x approaches c, right, of f of x minus f of c over x minus c.